Hi, my name is Gukjin Lee, who is working at reliability team in IMEG as a postdoc. First, thank you for listening this paper review, and today I will present the paper which will improve the metal contacts in tungsten deselenide transistor using hot carrier injection or partial thermal effect. Okay, let me start. Okay, this is our content for contact engineering and applications for 2D materials FATs. And first of all, I mainly refer the detailed book and Adrian's paper in 2015. Yep, so this is the outline or introduction for our research. And first of all, I mainly, as you can see in the transfer curves variations, there are three different types of characteristics. First one is pristine before annealing and after annealing in high vacuum, like this, and especially after hot carrier injection, like this. So interestingly, after hot carrier injection, I called it as a partial thermal heating effect. The performance of device was significantly improved, even much more than after annealing in high vacuum process, like this. We applied a high negative voltage to drain electrode called as hot carrier injection, as shown in the band diagram on the right, like this. So then why did I apply a high negative voltage to drain and only for the 2 volt full gate? To be honest, it was obviously from my huge mistake for setting SMUs. Yeah, so I found this partial thermal effect after 10 seconds of my mistake. So let me start. Okay. The next one is the disadvantages of large contact resistance or degrading performance of devices, such as on current, subthreshold swing, or mobility and threshold voltage shift. And second of disadvantages is an inaccuracy of measuring and characterizing FETs. And then, why does a large contact resistance occur or form between the 2D materials and the metal? There are several reasons for that. First one is van der Waals gap, and second one is Schottky barrier caused by energy differences between the work function of metal and the electron affinity of the 2D materials. And third one is Fermi level pinning effect and exhibits kind of water or oxygen and chemical residues and carbon contaminations when we use deposition or measuring, or finally, or high energetic metal atoms can be damaged to the sheet, so it can make any large contact resistance between the metal and the 2D materials. Then in this slide, let me talk about the Fermi level pinning effect. Normally, when the metal and the semiconductor attach each other, Schottky model relationship should be satisfied, right? Like this, it should be satisfied. However, some factors such as surface states or metal-induced gap states or defect states or disorder-induced gap states can make form a special potential which gets out of the Schottky relationship like this. This phenomenon large occurs in contact between the 2D materials and the metal. Yeah, so it makes this potential, so it gets out of the Schottky relationships. So we talked about disadvantages and why this large contact resistance is occurred, then let me talk about how can we improve the contact resistance. If semiconductor was three-dimensional bulk material, we could improve through doping to bulk semiconductor in usual case. However, in 2D materials, it's difficult to dope, and they have few dangling bones, and it cannot make strong interference with metal. Therefore, large contact resistance is formed instead. And there are two ways to make contact between the metal and the 2D materials. First one is top contact method like this. In fact, edge contact, as shown like this, has no van der Waals gap unlike top contact. So designed edge contact between the graphene and the metal is reported in 2013, and it showed shorter bonding distance with a large orbital overlap, like a strong hybridization. So as a result, contact is improved rather than top contact. But as we know already, when we form contact, top and edge contacts are both formed, and the surface of the top contact has larger surface area to edge area ratio. So top contact has larger contribution rather than edge contact, rather than that of edge. So yeah, as you know. Okay. So first, then how can we improve the top contact resistance? First, we use some metals which can make a strong hybridization effect. As a representative example, we can use tight contact for molybdenum disulfide, and this metal can make covalent bonds with a strong interaction. And there are some other combination with have a strong hybridization, which have nickel, graphene, or titanium with a molybdenum disulfide, and palladium with a tungsten deselenide, like that. Next, we can also use thermal annealing treatment on TMD devices, like 2D devices. In previous study from Wei in 2014, when devices are post-treated by thermal annealing, improved contact resistance, which is rigidity-free and has a strong hybridization is formed. So it has improved contact resistance when after thermal annealing effect. Besides, there is some interesting report of it. The first one, when the contact metal atoms are deposited on the TMD surface, a high bombardment energy of them may get damage into the 2D channels, to the sheets. It resulting in a bad quality of the interface between the metal and the 2D sheet, 2D materials. So Yang Ryu transferred the contact metal on the TMD channel without damage from deposition, and he satisfied the Schottky relationship through this method. So it's very interesting research. And we can also use the ultra-high vacuum metal deposition or the interlayers such as graphene in order to improve a large contact resistance like that. So you can see these previous studies. Before the experiment method, I will introduce some theoretical background for this paper. The first one is Schottky Barrier height is generated at the interface between the metals and the semiconductor or PN junctions, and they limit the carrier movement or injection. So I use this formula for this paper. And the charge injection mechanisms is very important to understand. So charge injection mechanisms through Schottky barrier can be explained by three ways. First one is thermionic emission, and thermionic field emission, and field emission. And thermionic emission is charge injection when the energetic carriers which have same or higher energies comparing with effective barriers, effective barrier height. And field emission, also called as a quantum mechanical tunneling, the carrier which is wave nature generates charge injection by penetrating the thin barrier. Finally, the thermal field emission gradually contributes as doping concentration increases. And there are three ways to extract the barrier height. In this paper, we use approximate barrier height through current voltage method. Although Richardson's constant in natural logarithm, Richardson constant is in natural logarithm like that, so it makes small errors, but uncertainty from this Richardson constant makes some error for that. But I don't have any condition for measuring with temperature variations, so it was only allowed to use previously stated Richardson constant of tungsten desalinized. So I just need some variations or change just a little bit for before and after the hot current injections or thermal treatment effect. So I just need a approximate Schottky barrier height. It's just the differences between the before and after. On the other hand, we can use current temperature method in temperature variations. It's widely known as you guys. And we can extract effective barrier height with an error correction from Richardson plot like this. And we need different current measurements with different temperature, and through this we can make a correction of Richardson constant. Use this formula. So in this paper, we use two methods for extracting or calculating contact resistance. First method is for probe method using innocence electrodes, as shown in optic image like this. In this method, innocence electrode like this measure the voltage in here, while outer electrodes are applying current source. From this, we can extract the channel resistance and also calculate the contact resistance. So I think this is very powerful method. But in the Chris paper, there's some problem because some shunted current like this in this figure could be induced by, in a sense, electrode like this, and this electrode can make a doping effect to channel surface. So it's much better to use narrow inner electrode in a sense contact like this, very small contact, as shown in optic image like this. Yeah, and I also use the Y function method, and Y function method is normally used as a methodology, and this method is widely used at like transmission line method using a length split. And through this, the mobility attenuation factor and contact resistance could be fitted, and contact resistance is also calculated from this fitting. In this experiment, however, we suppose the intrinsic mobility attenuation factor set 10 was almost zero and extracted contact resistance approximately. Yeah. Finally, let me talk about the experiment of this paper. You take a long time for experiment part. So, and the channel thickness of the tungsten disolenoids was 14 nanometers, which indicated 18 layers of tungsten disolenoids. And pristine device has 9.655 volt per decade of the threshold swing, and after annealing in 200 Celsius 2 hours and high vacuum, the performance of device was improved a little in like a black dot, but not dramatically as shown. But after hot carrier injection, as I call as partial thermal annealing effect, the device was highly improved, like dramatically with a 0.562 volt per decade of subthreshold swing. And also extracted contact resistance was highly improved after partial thermal treatment rather than high vacuum annealing that we treated before the partial thermal treatment. Yeah, it was very interesting. So, yeah, mate. I think you never see this SEM image because uh, I've never reported this SEM image on the paper or something else. But I think this SEM image could be very helpful to your understand. So I just set this image in. So interestingly, this kind of partial thermal annealing effect is maintained even after 10 days, almost maybe, yeah, so almost maintained. And the difference of brightness contrast in SEM image occurred only around measured electrodes and the channel like this. It's very interesting, right? So I think the summer partial Joule heating effect could be generated, especially in the after the measuring after the hot carrier injection. So yeah, finally, so we can expect the partial Joule heating could be a main factor of this experiment. However, when we apply the high gate voltage into device, also high gate voltage, and also of course drain voltage into the device, the carrier concentration was increased. So many carriers involved as a hot carrier injection, so resulting in burning devices as shown in a right SEM image. Yeah, so this is very important part of carrier injection, asymmetry carrier injection. We also investigated output characteristics, IDVD, as a function of drain voltage. And they showed a symmetric carrier injection properties after a vacuum annealing, but changed into like a symmetric carrier injection after hot carrier injection or a partial thermal effect. So as I mentioned in previous slides, effective barrier height of channel only for near source electrode lowered by partial thermal treatment like this. And in this study, we also used two methods for confirming this phenomena. We measured surface potential through the EFM, and the surface potential of channel near source electrode was lower than of near the drain electrode part. However, we couldn't find any variations of IFM height, so there is no any burning effect or burning effect or the etching effect in here. And through Raman spectroscopy mapping, we analyze peaks as central like this and point near the source or point near the drain. There was no change in E2G or A1G peaks. However, there was a peak shift in only B2G peak, only near the source. Through this, we could confirm there was a change of train in outplane directions. So this is the previously studied in the Zhao. To be honest, I really wanted to find optimized condition for performance enhancement. So like kind of do TEM images or optimize the hot current injection conditions, gate voltage, drain voltage, or time for performance, best performance. And the other, I want to check the other TMD materials, kind of molybdenum disulfide or uranium disulfide or tungsten disulfide like that. Or I want to do reliability test like a TDDS, and I want to do other contact metals like nickel or chrome or gold and silver or platinum. So I want to check the Schottky mud low. And the final one, I really want to check the temperature independent barrier height measurement. So I think you guys have a chance to check this out because I don't have any facility or equipment in the device or fabrication process in IMEX. So I think you have a chance to do this. Yeah, thank you for your attention. So this is all. Yep, thanks. See you later. Bye.